So let's briefly recap that we are looking at the eigenvalue problem of J square and J3. So we're simply characterizing the eigenvalue of J square as alpha and the eigenvalue of J3 as beta. Okay. And whenever I say that these are the eigenvectors, trivially this means that in this basis, in the alpha beta basis, the matrices for J square and J3 are diagonal. Okay. So remember that J square is a Hermitian operator and J3 is also a Hermitian operator. And as we already know, eigenvectors corresponding to distinct eigenvalues of a Hermitian operator are orthogonal to each other. So you should have alpha prime beta alpha beta is equal to delta alpha prime alpha, because alpha corresponds to the eigenvalue of a Hermitian operator J square. And similarly, this should be delta beta prime beta. Okay, so I can combine these two relations and say that these states are normalized in this fashion. Okay, so this is a straightforward application of the fundamental theorem regarding Hermitian operators, that their eigenvectors are always orthogonal corresponding to two distinct eigenvalues. Okay. So the question is, on this basis, what do J1 and J2 do? To understand the actions of J1 and J2, we form the linear combinations J plus minus, J1 plus minus IJ2. And we found that the action of J1 can be understood by looking at the commutation between J plus and J3. And we found that J plus effectively raises the beta value by 1 unit of H bar. So we found that J3 acting on J plus alpha beta is simply equal to beta plus H bar times J plus alpha beta. Okay, so this is where we roughly stopped last lecture. This means that the state J plus alpha beta, whatever this state is, because this is an operator acting on a ket, which is again a ket. So this ket is such that it is an eigenket of J3 because it is of the form J3 times the ket equals some number times the same ket. So this is obviously an eigenket of J3, but it has the eigenvalue beta plus H bar. But you already know all the eigenkets of J3 because they are simply the alpha betas, right? And the eigenvalue is beta. So through this logic, you conclude that this ket J plus alpha beta, that is an eigenket of J3 with eigenvalue beta plus H bar, has to be proportional to beta plus beta plus H bar. Okay, and then we wrote down the relation J plus acting on alpha beta equals some C plus some coefficient times alpha plus H bar. Okay, so this is I think roughly where we stopped. Now look at this relation carefully and notice that you could not have guessed this relation unless you knew about the commutation relations. Why? Because remember how you look at vector space, linear vector spaces in general. If you have two matrices that do not commute, and if you write everything in the eigenspace of one of the matrices, then the action of the other matrix on this, in the basis vectors of the other, the second matrix would be in general some linear combination of the matrices, right? So suppose if I did not know about the commutation relations, and if you had asked me how do J1 and J2 or equivalently J plus and J minus act on this Hilbert space, I would have said, oh well, J plus acting on alpha beta would give you some linear combination of all these states, right? Because that is how we approach linear operators in general. A linear operator acting on some set of basis vectors would give you in general some linear combination of the basis vectors. Of course, we find because of the special angular momentum commutation relations that it doesn't, J plus acting on alpha beta doesn't give you a linear combination of all the beta states. It only gives you one exactly one state with eigenvalue beta plus h bar. So this, you have to appreciate that this is precisely due to the angular momentum algebra. Okay. So obviously this also tells you that the eigenvalues of J3, so we can also guess that the eigenvalues of J3 are multiples, integer multiples of h bar, right? Because you go from one state to the other, you go by raising one factor of h bar. Similarly, even though we did not prove it explicitly in class, you can go through the exact same exercise for J minus. So you calculate the commutator of J3 and J minus, and you would find that it is equal to minus h bar J minus. And then you would find that for the J minus operator, you would have the corresponding statement J minus alpha beta equals beta minus h bar times J minus alpha beta. Okay. And by the same logic, we conclude that the ket, whatever this ket is J minus alpha beta, is also an eigenket of the J3 operator, but this time with eigenvalue beta minus h bar. Okay, so then we conclude that J minus alpha beta, this ket should be proportional to the ket beta minus h bar, and we write J minus alpha beta equals some other proportionality constant C minus times alpha beta minus h bar. Okay, so let us collect all we know about this Hilbert space that we have just understood. We still don't know exactly what the eigenvectors are, or what the matrix form of, or equivalently what the matrix form of these different operators are. We will get there. But notice that we have understood an awful lot by simply looking at the eigenvalues. So we found that for a given alpha, there can be a range of betas. Okay. Remember that for all these different kets, alpha is the same. Why? Because alpha j square commutes with, since j square comma ji equal to 0, we have j square j plus minus is also equal to 0. Right? So the alpha value, which is the eigenvalue of j square, does not change between simply by application of j plus. Okay. So let's actually show this explicitly.
Hello, sir.
Yes.
Sir, I don't understand that argument that eigenvalues of J3 is multiple of H.
So
Because of, sir, thing is that here when I am operating J minus on alpha beta, okay, I am then I am getting that my beta is increasing by H prime, okay, but I don't know the value of beta here. So shouldn't be there something like that? There's some constant plus integral multiple of H.
No, I'll come to that in a second. Okay. So let us actually first show that this is actually true. So what I mean is the following. So let us say that you have some state alpha beta, and then you act j plus on this state. Okay. Sorry, excuse me. Some state alpha beta, and then you ask what is the j square value of this state, and you know what the j square value of this state is. You simply act j square on this alpha beta, and you get alpha times alpha beta, and you say that this state has j square eigenvalue alpha. Now suppose if I look at a state j plus alpha beta, okay, of course this state j plus alpha beta is equal to some c plus times alpha beta plus h bar, but suppose if I simply ask what is the j square value of this state, j plus alpha beta, I add j square on this guy. Okay, but since j square and j plus commute, I might equally well call this as j plus j square alpha beta. And since j square alpha beta is just alpha, I know that this is alpha times j plus alpha beta. So you see that the state j plus alpha beta is also an eigenvector of the j square operator with the exact same eigenvalue alpha. Okay, so the j plus acts in such a fashion that it raises the beta value by 1 unit of h bar, and j square acts in such a fashion that the j plus alpha beta does not change the alpha value of the state. So what you have basically is a series of states. You have some alpha beta, Okay, and then you can keep applying the J plus operator, and you keep increasing the beta values by 1 unit of H bar. So on and so forth. Okay, and then you keep decreasing the beta value by 1 unit of H bar by applying the J minus operator, and so on and so forth. Okay, now let us ask what could be the value of beta, because we are this is our Hilbert space. This is our set of basis vectors. These are basis vectors because these are the eigenvectors of Hermitian operator. So I can always use them as basis vectors, and they'll be tremendously useful in angular momentum problems. These basis vectors. Okay. So now, what could be beta? Well, remember that I could have simply started by by measuring J square and J3 in units of H bar, because H bar is the units of angular momentum. So instead of starting this way, instead of starting by saying J3 acting on alpha beta is beta times alpha beta, I could have as well started by saying this is equal to beta H bar alpha beta. Okay, I could have made it explicit that I'm measuring everything in units of angular momentum, and I still do not know what beta is. That was the question. Okay, but it is some measure of angular momentum, so there has to be some H bar in there. So from dimensionality, I could have started by saying that this has to be beta times H bar. And if I had started this way, it would have been easier for you to see that once I apply the J plus operator, it simply increases the beta value by 1 unit. Okay, so suppose if I started this way and I applied J plus on alpha beta, I would have found that this is equal to something times alpha beta plus 1 instead of beta plus H bar. Okay, so since this beta value, and similarly, if I acted J minus on this state, I would have found that this is alpha beta minus 1. Okay, so this was simply a matter of either writing the H bar initially or not writing the H bar initially. Both are equally okay because you will get the exact same final results. But if I had measured angular momentum units of H bar straight away, I could have easily seen that I am raising and lowering the beta values by 1 unit. Okay, by a number, which means the beta has to be an integer, because so suppose if let us say that I start with some value of beta, okay, and then I go up this ladder and down this ladder, and I only increase by units of 1. Okay, now you could still argue that the initial value of beta could be 0.3333, okay, and then you will increase and decrease. But there is 2 arguments against it. The first argument is a very practical argument. Always you measure everything against experiments, okay, and then you look at what the experiments tell you. You look at what the world looks like, and you actually find that there is no particle in the world that has a spin of 0.3333. Okay, so this is ruled out by observations. So the only possibility that the world demands, the world imposes on you, is that the beta has to be an integer value. But of course, it's not completely right, because as we will see towards the end of this lecture, there is actually 2 different kinds of values of angular momentum values that are admissible. One are integers and the other are half integers. We will see how that falls out in the algebra. But any other random value of beta is excluded simply by observation. Okay, so anyway, I started by just beta instead of beta times H bar, because I wanted to stick with Shankar's notation, but I think beta times H bar would have been a more logical starting point. Anyway, it doesn't matter. So this is the kind of Hilbert space that we seem to be getting.
Sir.
Sorry, just one second. I'll have to stop this and share it again. Yeah, please ask your question.
Sir, you had said that beta takes only integer values, and is that provable, or is it just an observation that we make? Is there no mathematical derivation or proof for that?
Mathematical derivation of proof. I will think about this if there is anything fundamental that tells you that beta has to be an integer at this state. But it seems rather contrived to have any random value of beta, right? Because you're only changing beta by 1 unit of H bar. as you go up and as you go down. So it makes much more sense for beta to be just an integer, some multiple of h bar, some integer multiple of h bar. And also from your discussion of on orbital angular momentum, this should not be very surprising, right? There we actually showed that beta should be an integer multiple of h bar. Of course, this is not orbital angular momentum. This is a little more general. So I will think about this question and get back to you guys if there is anything more fundamental that I can think about. Okay. So let us actually, since I talked about orbital angular momentum, let me also sort of refresh your memory there. So there we actually discussed, so aside. So when you talk about orbital angular momentum, remember that your YLM of theta phi's, which are the eigenfunctions of the orbital angular momentum, we wrote them as some PLM times e to the im phi, right? Sorry, PLM of theta times e to the im phi. And the fact that m here, which is the eigenvalue of the L3 operator, the fact that m has to be integer came about by demanding that the wave function be single valued. So we said that if I go from phi to phi plus 2 pi, my wave function has to be exactly the same. So this imposed the constraint that e to the 2 pi m has to be equal to 1, which told you that m was an integer. Okay, so this was an orbital angular momentum. So there is no such thing here because we are not working with wave functions. We are just working with abstract operators. And also, I will also use the same symbol m here. I'm sorry about that, but I don't mean the m that appears in the orbital angular momentum commutation relation. So some books actually differentiate this by putting an m sub l here for this guy. Okay, which tells you that this is the m for the orbital angular momentum part and does not include the spin. But I will try to avoid this notation, but I will use this notation only when I absolutely need to use it. Okay, so if you actually look at this ladder, this is, as somebody rightly pointed out yesterday, it looks somewhat like the simple harmonic oscillator problem that we discussed, with one crucial difference. In a simple harmonic oscillator problem, even though there was raising and lowering operators, we asked the question that does this ladder end somewhere, right? And we found that it did end, they did have a lower limit, but there was no upper limit as such in the simple harmonic oscillator case, right? So in the simple harmonic oscillator case, so simple harmonic oscillator, again, remember that you had some n, and then you could go up by acting on by the a dagger operator and go to state n plus 1, n plus 2, and so on and so forth. Or you could act by the state a and go to state n minus 1, n minus 2, and so on and so forth. And we found that this ladder has a lower limit. And this lower limit came by imposing that the Hamiltonian be bounded from below. Okay, otherwise you will just keep going infinitely low, and then you will create states of highly negative energy and the system would be highly unstable. So by demanding that the Hamiltonian is bounded from below, we stopped the ladder at some point, and that point was n is equal to 0. So this was the ground state of the simple harmonic oscillator. You cannot have anything lower than that. So that was the physical argument used to restrict the simple harmonic oscillator ladder, but there was nothing that was used to restrict the ladder going up. So I can put in as many particles in the state as I want. Okay, and we also argued that this has to do with the fact that these are bosons. So
hello, sir.
Yes.
Sir, here I am working on the angular momentum. So how Hamiltonian is involving here?
No, I'm not talking about Hamiltonian. I'm simply reminding you of a corresponding problem in simple harmonic oscillator.
Oh, okay.
We will now ask the same question in the in the angular momentum case also. So here also we seem to have something very similar, right? So we start from the some state and then you apply some raising operator and go up, and apply the lowering operator and go down. So we will now ask the exact same question we asked in the harmonic oscillator problem. Does this ladder end somewhere? Okay.
Okay, sir.
So the question is, does it end somewhere? And it turns out in this case that it does end. And unlike in the simple harmonic oscillator case, this has both an upper limit and a lower limit. Okay, we'll understand how that comes in. So before understanding how that comes in, let us actually look at this picture sort of naively from a classical mechanics standpoint. What does classical mechanics tell you? Well, J3 is the third component of angular momentum, and J square is the total angular momentum, right? So which means that the square of the total angular momentum should always be greater than the square of the third component of the angular momentum, right? So in other words, if you simply look at it from a classical perspective, you would find that the J3 square should always be in some sense less than J square, because J square is J1 square plus J2 square plus J3 square. And J1 square is manifestly positive, J2 square is manifestly positive in classical mechanics. So of course, J square should be some quantity that is greater than J3 square. In other words, classical mechanics would tell you that alpha should be greater than beta square. Okay, so let us look at the corresponding statement in quantum mechanics. So in quantum mechanics,
Hello, sir.
yes.
Sir, can we have the case in which J1 square and J2 square can be 0, or should they always be a value greater than 0, sir?
In classical mechanics?
In quantum mechanics, sir.
No, in quantum mechanics, these are operators. So these are well defined.
Okay.
So they are not null operators, right?
Okay,
So these are positive definite operators. J1 square is positive definite operator, J2 square is positive definite operator, which means J1 square plus J2 square is also a positive definite operator.
Okay, okay, sir.
Okay. So in quantum mechanics,
sir,
yes.
sir, I had this doubt that you assume that J3 acting on alpha beta is equal to alpha times alpha beta cat. Okay, and then same for J square. You assume that beta times alpha beta cat. Sir, and then after that we reduce that on that J plus this J3 is something the eigencat of J plus, or the relations out of which we assume we concluded that this J3 J plus or some the operator that was written, it would then go for alpha times beta minus h bar cat, right? So sir, but you assume there in the J3 and J square that the eigenvalues will be alpha and beta respectively. Sir, isn't that some kind of a a trick kind of thing that we assume the alpha and beta is the eigenvalues? If we had assumed, like if I had represented it by some C and C2, C1 and C2, how would I have guessed that this, if I get the on operating that J plus on them, I'm getting C plus minus H bar. Then how would I assume that the eigencat would be alpha times eigencat would be alpha beta minus H?
Okay. So there is no trick. So the issue is actually, it is very simple matrix algebra if you want to look at it that way, right? So let us say that you have a set of 4 3x3 matrices, right? So let us call this A, B, C, and D. Okay. Oh man, so sorry. I'll have to reshare. Sorry, just give me 1 minute. Okay. So let us say that you have 4 3x3 matrices, right? So forget about operators and things like that. And let us say that this matrix is such that A commutes with all of them. Okay. While B, C, and D do not commute. All right. So there is BC is not equal to 0 and so on and so forth. CD is not equal to 0 and BD is also not equal to 0. Right. Now I want, so these are all 3x3 matrices. So I'm talking about a 3-dimensional linear vector space. And I want to understand this linear vector space, 3-dimensional linear vector space, by choosing some basis vectors. So how should I choose my basis vectors? Well, if I choose a random X, Y, Z, P or 1, 2, 3, 4 axis, then if I choose some random axis like 1, 2, sorry, this is 3 by 3 matrix, so there's a three-dimensional linear vector space. If I choose x, y, z or 1, 2, 3, then the action of A, B, C, and D on this linear vector space is always going to be complicated, because A acting on some EI or A acting on 1 would give me some A1 times 1 plus A2 times 2 plus A3 times 3, right? Similarly, B acting on 1 would also give me, so everything would mix up everything else. So the action of A, B, C, and D on the 1, 2, 3 vectors, the usual one, so if I choose this to be 1, 0, 0, 0, 1, 0, and 0, 0, 1, the action of A, B, C, and D on all these vectors would in general give me some linear combination of all these vectors. Now, there is nothing fundamentally wrong about that, but we want to make our lives easier. The way we make our lives easier is by choosing a slightly more convenient set of basis vectors. The way you choose a more convenient set of basis vectors is by saying, look, if I can choose the the basis vectors to be the eigenvectors of these guys, then if, for example, if one happens to be the eigenvector of A, then this part and this part won't be there, right? So the action of A on this vector would be very simple. So it's always useful to choose the basis vectors to be the eigenvectors of at least one of the matrices. Now, in general, if you have a whole bunch of matrices, you choose the common eigenvectors of as many matrices as possible. Okay. So in this case, suppose if I, let us say that instead of 1, 2, and 3, I'll have some, let us say alpha, beta, gamma. And alpha, beta, gamma are the eigenvectors, simultaneous eigenvectors of, let us say, A and D, which is what I'm choosing. So which means that, or let us say alpha 1, alpha 2, alpha 3, maybe that is easy. So all I'm saying is that A acting on alpha I is just some number times the same vector, nothing else. Yes, any questions?
Do you mean that if I'm getting it right, then if a matrix is in its eigenvectors, then the eigenvectors would be the columns and the eigenvalues would be on the diagonal. So
Yes, but that is only if I express the basis vectors as the eigenvectors of the matrix. See, if I express them, so what is meant by diagonalization of a matrix? When I say I want to diagonalize a matrix, I mean the following. So I am writing the component. See, just like the components of a vector depend on the basis vectors that you choose, the components of a matrix also depends on the basis vector that you choose. So you could be working with a set of basis vectors in which the matrix is not diagonal. But suppose if you were instead working with basis vectors as the eigenvectors of this matrix, then in that matrix, in that basis, the matrix will be diagonal. That is the whole point of diagonalization, right? So instead of one matrix, what happens if you have a whole bunch of matrices? Well, the linear algebra tells you how to solve this problem. It tells you that, look, if you have a whole bunch of matrices, then you cannot be completely happy, because you cannot have a basis vector in which all of them are diagonal, because some of them need not commute with each other. So you simply collect all the matrices that do commute with each other and write down the common set of eigenvectors as the basis vectors. So that is what I'm doing in this case. So I'm collecting the common eigenvectors of A and D, and that is just a choice. I can collect the common eigenvectors of A and B or A and C, but I'm collecting the common eigenvectors A and D, and this would be such that, so this basis is alpha 1, alpha 2, and alpha 3. And the advantage of, oh man, my Bluetooth is really misbehaving. I'm sorry about that. So the advantage of this basis would be that the action of A and D on the vector space, on the basis vectors, is actually very, very simple. It simply tells you that A acting on alpha 1 is just something times alpha 1. And D acting on alpha I is just some other eigenvalue. It could be some beta I, but it's just alpha I. Okay. Now you can ask, on this basis vectors, what is the action of B and C? Well, B acting on alpha 1, since B will not be diagonal anymore, B would be giving you some C1 times alpha 1 plus C2 times alpha 2 plus C3 times alpha 3. And then you can ask, what is C acting on, let us say, alpha 2, and this will again give you some C1 tilde times alpha 1 plus C2 tilde times alpha 2 plus C3 tilde times alpha 3, right? So the action of the other matrices on the basis vectors of a different matrix would in general be a linear combination of the basis vectors. So that this is exactly the point that we are trying to do. In the case of j square and j3, so instead of A, think of j square, and instead of B, think of j1, C, think of j2, and D, think of j3. All I'm doing is that I'm diagonalizing j square and j3 simultaneously, and then I'm looking at what the basis vectors are. Okay, so the basis vectors, so sorry, what the eigenvectors are, because these eigenvectors I can use as a basis vectors to understand the action of all these different matrices. Instead of looking at any random vector space, I will look at a vector space where the basis vectors are the eigenvectors of j square and j3. So in this vector space, the action of j square and the eigenvectors alpha beta is very simple. J square acting on alpha beta would simply just give me the same vector back. Similarly, j3 acting on alpha beta would simply give me the same vector back. But j1 acting on alpha beta would in general give me some linear combination of all the alpha prime beta prime, right? So see alpha prime beta prime, just like this guy and this guy, right? But we actually found out by the commutation relations that this is actually not true. It doesn't give you any linear combination. It will only give you one particular state. So that is a result of the commutation relations. So no, there is no trick. This is simply an application of very basic linear algebra, that if you have a bunch of matrices, then it always makes sense to choose as your basis vectors the eigenvectors of the maximally commuting set of these matrices. And in this case, the maximally commuting set of matrices is just 2. Okay. Suppose if I'm looking at rotations in not 3 dimensions, but 4 dimensions or 5 dimensions or 6 dimensions, I can have more number of matrices that commute with each other. So on and so forth. Does this make sense or no?
Yes, sir.
Okay. Okay. So let us actually understand if this ladder has a beginning and an end. Okay, so we will figure this out and then stop for the day. So the way you understand this is by looking at the quantum mechanical version of the statement that J3 cannot be larger than J square, or rather J3 square cannot be larger than J square. So you start with the J square operator. So this is equal to J1 square plus J2 square plus J3 square, right? And then let us look at the expectation value of this operator in the state alpha beta. So obviously this is equal to J square acting on alpha beta is just alpha beta. So this is just equal to alpha, right? But I can also write this as alpha beta times J1 square plus J2 square plus J3 square alpha beta. So now let us look at this particular guy. So this is equal to alpha beta J1 square plus J2 square alpha beta plus alpha beta J3 square alpha beta. Right? Now I do not know in general exactly what this is, because I have not yet calculated C plus and things like that. But this is some positive number. This has to be some positive number, because J1 square plus J2 square is a positive definite matrix, positive definite operator. So this is some number greater than or equal to 0. And this number you know exactly. This is J3 acting on alpha beta is beta times alpha beta. So J3 square acting on alpha beta is beta square. So this is beta square. So you get the relation that alpha equal to some number greater than or equal to 0 plus beta square, which tells you that alpha minus beta square should be greater than or equal to 0. Okay, so this is the quantum mechanical equivalent of the classical mechanics statement that the angular momentum J3 square component cannot be larger than the total J square. Here it is saying that the angular momentum eigenvalues are such that alpha minus beta square should always be greater than or equal to 0. So beta square can at most be equal to alpha, but it cannot be greater than alpha. Okay. So we will use this particular constraint to understand how to terminate this ladder, both at the top level and the bottom level. So one cannot indiscriminately keep increasing beta because beta square is bound by alpha, right? So at some point you're going to violate this constraint because you start with some state with some particular beta, increase the beta by 1 unit of h bar, you keep going, beta plus h bar, beta plus 2 h bar, beta plus 5 h bar. At some point, beta square would be greater than alpha and violate this constraint. So you have to stop the ladder at some level up top. Similarly, you keep going down in the bottom. You start with some beta value and go to beta minus h bar, beta minus 2 h bar, beta minus 3 h bar, and so on and so forth. And at some value, you're going to get some highly negative value of beta. But since this relation depends on beta square, this highly negative value would also violate this constraint because alpha minus beta square would be not greater than or equal to 0 anymore because beta square can become greater than alpha. So beta cannot become very highly positive or very highly negative. It is, excuse me, bound by the value of alpha. So we conclude that one cannot keep increasing this is a horrible day for Bluetooth. Increasing or decreasing the value of beta indiscriminately because we will violate the constraint alpha minus beta square is greater than or equal to 0. So let us assume that there is a state in this Hilbert space. So there is a state with a maximum value of beta and a state with a minimum value of beta. Okay. So now if I redraw this Hilbert space, how it looks like, again you have the J square operator having an eigenvalue alpha, and you have all these different states alpha, beta. But now I have a top state alpha, let us call this beta max. Okay, and then I apply the J minus. So okay, let us start from some state alpha beta. Okay, just as before. And then I apply the J plus operator and I go to alpha beta plus h bar, alpha beta plus 2 h bar, so on and so forth till I hit a ceiling. I don't know what the ceiling is. I'll call this beta max. Okay. Similarly, I apply J minus and keep going to the bottom. And I go to alpha beta minus h bar, alpha beta minus 2 h bar till I hit the floor. And the floor is some value of beta, which I will call beta min. So we'll have to figure out what these top and bottom values of beta are. Okay. All right. So to understand what these top and bottom values are, we will again follow a strategy very close to the simple harmonic oscillator strategy. So let us actually recap what the simple harmonic oscillator strategy was, and then we will actually do the problem out tomorrow because we're running out of time. Remember, in the simple harmonic oscillator, the way we understood this was by claiming that there is, again, you keep going up and down in n. So you keep going up in n by applying the A dagger operator, and you keep going lower in n by applying the A operator. But there, you didn't have a ceiling, but you had a floor. And you had a floor and you said that, look, there is a zero state such that you cannot go down any further, which means there is a state such that if you apply A on this state, you will identically get something zero. Okay, and this constraint told us what the state was. And similarly, we will have to employ a similar constraint here, and we have to claim that the ceiling is such that if I apply J plus to the ceiling, I will not get any other state back because that is the maximum it can go to. So I will get identically something equal to 0. So J plus acting on alpha times beta max is equal to 0. And then similarly, J minus acting on the floor alpha beta min would be equal to 0, because you cannot penetrate the floor and go down, because this is the lowest value beta can possibly take. Okay. So we will use these two constraints to figure out what beta max and beta min are. And then we'll talk a little bit about um, the construction and how the vector space looks like. And then we will apply it to the case of spin half, J is equal to 1/2. And then you will finally understand where the Pauli matrices come from. Okay, so thus far in your life, Pauli matrices were just something that was given to you, but we will explicitly derive the form of the Pauli matrices, and you will understand that they're just one special case of one special value of J. So this will be our homework for tomorrow. Okay, so for now we will stop here, and please ask if there is a